Okay, thank you everybody and happy Friday. Thanks for taking time to learn more about properly tuning your ammonia injection grid and how a permanent sampling grid can make the process even more efficient. We've had a lot of interest in this webinar and a lot of folks sign up. We appreciate everyone's interest and hope to answer all of your questions proactively here in the webinar titled Impact Your Bottom Line While Online. We're going to cover as much as we can here in the 30 minutes we have allotted in the body of our presentation. Once there are some questions that you might have that were unaddressed, we're going to have a 15-minute Q&A afterwards. Groome will be presenting alongside Environex here, and we hope everyone enjoys. Here we go. Okay, so some basic house cleaning. First, we're going to start off with AIG Tuning Procedure. Some people are very familiar with this, some not. So we're going to fill in the blanks there, define the process, procedure, features, and benefits. We're going to talk on some ways that you can make the process more efficient and accurate, including permanent sampling grids. It's a great technology and feature. In order to bring things a little bit more close to home, maybe help you identify with some issues that you might be seeing at your plant. We're going to go over 2 specific case studies where we helped different plants in different areas of the country with ammonia flow problems. Furthermore, we're going to discuss some of the findings and successes that we saw on those projects, up to including the ROI, so you can see what benefits you'll be able to realize, along with how much money you can potentially save. This session will be recorded, so if for some reason you need to hop off to address some other issue, not a problem at all. We're going to be sending the recorded link out to everyone, hopefully by tomorrow at the latest. My name is Steve Houghton. I'm the VP of Sales at Groome Industrial. I oversee the 5 divisions that we've got there, specializing in different things. Today, we're going to focus on the HRSG and refining side, and different units in that space. Andy Toback, project manager at Environex, has over 15 years of experience in hundreds of units in the industry. So we hope to be able to pick up some knowledge from him here as well. So one question that a lot of you folks might have signed up for this webinar that you might have is, why tune my AIG? Why is it important? The question I have for you here is, are you able to answer this question? Are your AIG and SCR working together, or are they working against each other? And AIG tuning, or proper tuning, will enable you to understand that. It's very important for your ammonia to be dispersed evenly across the face of your SCR catalyst. But what if it isn't? So to pose a quick example here for you, if your capital investment in your SCR catalyst is worth $250,000, 250 grand. So I understand that some of your catalysts might be worth more, some less on this call, but we'll use 250 as a basic example, round number. If 80% of that catalyst bed is seeing proper ammonia flow, that means that 20% of your capital investment in SCR is simply not working for you. The equivalent of $50,000 in CapEx is just taking up space at your facility. Now, inversely, on the other side of the coin, some of your catalyst is probably seeing too much ammonia. In this case, you're experiencing ammonia slip. If you're not familiar with what ammonia slip is, it's when there's too much ammonia in the specific areas of the gas path. The catalyst can't handle it. It goes through the catalyst, unprocessed, unreacted, and out the stack. Now you're paying for ammonia that isn't working for you. It's very common and quite possible that both of these issues are happening in your unit to your SCR and your AIG at the same time. There's some areas of the catalyst that are using too much and some that aren't getting enough. Tuning will properly address both of these problems. 4 ways. First, it'll lower your ammonia usage by minimizing slip. It will increase the useful catalyst life, in turn lowering your capital cost. It'll improve your ammonia distribution. In doing so, you're going to improve your NOx conversion as well. So now that we've addressed the basic definition of what a tuning is, I'd like to pass to Andy to review some more specifics.
Thank you, Steve. As the title suggests, ammonia injection grid tuning, something that you could perform online. Most of the time when we talk about improving efficiency of your SCR, it involves having the unit down during an outage, and it would be work that would have to schedule, around other outage work. Here, not so much. You're running, the only requirement would be that whatever load or flow that you're using in the beginning of the test, we'd like to keep it the whole time. What do we do to tune? We use the sampling ports that are located on either the inlet or the exit side of the SCR catalyst to create a testing grid similar to the drawing I have here on the right. The drawing on the right represents a 25-point testing grid that we've used, in an installation. We then take a stack testing probe, much like the probe used for a RAT or compliance test, to measure the oxygen, NOx, and ammonia at each one of those test grid locations. Based on these values, the valves seen on the left drawing are adjusted. In this particular drawing, the valve 5, for example, would control the entire row 5 on the drawing to your right. So the values along row 5 would dictate how you would adjust valve 5 on the picture on your left. After adjustments are made, more measurements are repeated until the best tune is the result. Let's take a look at what one of these traverse tests look like. Here I'm showing a 35-40 point traverse of ammonia. And this is what they look like. On the left, you can see the as found position where the ammonia slip at the SEMS was 4.5 ppm. We left this as found here because intuitively you would think, I'm going to put all my valves at the same position and then I should get the best dispersion of ammonia. And you could see that that wasn't the case. The RMS distribution here is over 30%. And I guess I should get into what RMS distribution is. That is a statistical measure that we use to evaluate how well the ammonia and NOx are equal before the SCR catalyst. For your reference, catalyst vendors typically guarantee their product to perform the guarantees that you need, the conversion requirement, between 10 and 15% RMS. So for this particular example, as found, we see a surface plot that has a varying degree of ammonia slip on the exit side of the catalyst, ranging from little to no measured ammonia to up to 8 ppm. And then for the success photo on the right, after we performed 3 traverse tests on this particular SCR, the final ammonia to NOx distribution was reduced to 11%, and the corresponding ammonia slip down to 2 ppm. And if you look at the bottom right, those valve positions are much different than just placing them all at an equal value and hoping for the best. Let's talk a little bit more about valves. Later, is your unit a good candidate for ammonia injection grid tuning? This particular graph we use that can equalize, what your application is. So you have a refinery application, do you have a turbine application? we have a diverse group here. And what I want to do to discuss this all on an apples to apples basis is refer to the NOx conversion required from your SCR, and more importantly, your ammonia slip as a function of the inlet ammonia fed. Let's look at some of the values in the red area, which would be your best tuning candidates. I've highlighted a unit that has 30 ppm inlet NOx and 2 ppm ammonia slip as the limit. That would correspond, if you're looking for 1 ppm of ammonia to convert 1 ppm NOx, that would correspond to about 7% in your ratio of ammonia slip over ammonia fed. And that's where that particular point lies in this graph. As you go in the exact opposite direction of this area, you basically are looking for less NOx conversion performance and more of an ammonia slip limit. If the highlighted 9 ppm inlet NOx, 2 ppm ammonia slip point towards the middle of this figure, that's your GE7F. So a lot of times the workhorse of the refinery cogen, or a very popular combined cycle turbine in the power generation world, is this GE Frame 7. Due to its location in this chart, this would not be a great candidate. But if you want to talk about, the H, G, and F units, most of their design conditions are in the yellow and red areas. And in refinery applications, I've seen some furnaces and crackers recently that range of a NOx conversion of 87 to 95% with 10% ratio of ammonia slip over inlet ammonia. And you could see where that would fall in this graph. It would be near where the 4 is on the 45 ppm inlet slip. So those are all great candidates for ammonia injection grid tuning. If, let's say you're a great candidate, there's a few prerequisites that you need to happen before we can get into the ammonia tuning itself. And that's what I want to talk about here. It's got to be clean. So if there are nozzles that are plugged in your AIG and you go to tune, that's going to impede in the tuning process. And then what would make that matter worse would be subsequent cleaning afterwards. So now you've tuned the valves with, maybe only 60% of your nozzles open. You go to a mode where you're now clean, that tune has been negated. Up on your top left of the photos I've provided, you can see a lot of rust and slag. That's inside of an ammonia injection grid lance that we cut open for this, for the purpose of showing you the kinds of debris that are found in an AIG. In older installations, they're plagued with carbon steel upstream of the AIG, which is typically stainless. Well, all that carbon steel will rust over time, and that's some of the debris that you could see within this cutaway shot here. The middle photo I just experienced recently. So I was tuning a grid out west, and you can see how sunny we are. And we had a whole zone that wouldn't react to any kind of nozzle change. So we took the unit down and took a look at it, and you could see sitting on the orifice plate like a frying pan is a 2-inch by 1-inch brick of catalyst depositing. This particular unit received a bad batch of ammonia, and it ended up fouling every available surface it could find. So that would explain why none of the valve movements were working to tune this particular unit in, which is the next thing that needs to be in working order. So before we would want to get started tuning, we just want to make sure that the valves work, and often overlooked, that the flow gauges next to the AIG valves are functioning. We need to know, the effect of a certain degree of valve move and how it impacts the system. And then the bottom photo, just for, showing you what it should look like, is a picture of a clean AIG nozzle. I'm going to leave it next to Steve to talk about ideas of what to do when you don't have room to get the stack probe into your HRSG or existing SDR duct.
And so in listening to Andy there, you try to picture tuning with your traditional method using glass probes. Some units have ample access, while some don't. In order to gather proper samples, some of these probes are 10, 15 feet long. You have to ask yourself and look at your particular unit and understand, is that even possible to get a proper sampling in my unit? Can I access points that close with everything that's outside of the unit that might be restricting space? A permanent sampling grid can certainly address this issue in a permanent fashion. Many times we're installing a permanent sampling grid in concert with an SCR replacement. So it's easy enough to install. We do not need a major outage to complete this work. And just to define in layman's terms, as you look at these pictures, what exactly is a permanent sampling grid? It's essentially a network of stainless steel tubing on the exit side of the SCR catalyst. It's a planned grid of sample ports to displace that cumbersome manual probing process that we just described. Key word here that it's permanent. There's no more need once you set one of these systems up for invasive, time-consuming probing. It's also important to understand that not all AIG tunings are created equal. A permanent sampling grid makes it an economical investment, which allows you to sample from multiple points in each tuning zone. It also adds clarity to where your ammonia mix needs to be improved. You can also imagine that it makes the tuning and sampling process much faster and more precise. Just for clarity, to understand what that top picture is, you can see the stainless steel tube pointed in 90 degree. That's one of the 48 sampling points just downstream of the SCR catalyst on an install. That port corresponds directly to one of the test ports on the manifold, which you see in the middle picture. It's very important to note that these manifolds and the system itself is run outside the ductwork. This is very important because it restricts moisture from building up in the sampling grid. That moisture, if it's present, could more than hamper your test results. One last thing is it might look like an extravagant setup, but it's certainly not. It's not expensive. And again, you don't need a major outage to install one properly. The ROI, which we'll go over later, is pretty impressive. Quick visual, and I like this one because it relates the design of a system on the left with the basic CAD drawing with the corresponding ports and manifolds outside to the heat or traverse map on the right. The heat map, the way I like to kind of explain that is it just provides a more high def image of what your system's balance looks like and then what it could look like. This allows tuners to improve it drastically and more accurately. Now, how exactly is a permanent sampling grid better? It's faster and more precise, which allows for $20,000 in savings per tune. This provides a break even in 2 to 3 tunings, plus all the other system benefits such as NOx conversion, slip improvement, etc. Now, we've spoken in general terms on the process so far, procedure, etc. Now it's time to talk on some specific projects which you might be able to relate to. First one we're going to talk on is a 501G HRSG unit. Andy?
I brought 2 examples today, more for the interest of time, but we've had great success in tuning a lot of these units. I wanted to start with one of the old Mitsubishi Gs. There's about 10 of these left And we've been in a handful of them and have made great improvements. This case study also involves replacing the SCR catalyst and upgrading the ammonia injection grid. And then we followed up with tuning, which is more of what this particular case study is going to get into. The results were great. So before the outage, this is original catalyst and original AIG, the unit had a ammonia flow rate of 61 gallons an hour. Now, for NOx conversion, we're going to be chasing the same number all the time. They kept the same set point. But ammonia slip was climbing up toward 10 ppm. After just replacing the catalyst and maintenance, we were able to reduce ammonia consumption to 56.4 gallons per hour. And that corresponded to a 5 ppm slip. Then with tuning, we got an additional gallon an hour save and lowered the ammonia slip another per ppm. So now we're way far away from what the ammonia slip limit is for this particular unit, and satisfies a rule of thumb that we have about catalyst replacement. If your ammonia slip limit is half of what it is at the time, what your limit is at the time of catalyst replacement, that's a good place to start. If you're at 3/4 to 90% of your ammonia slip limit, while starting up, or a new installation or a retrofit, this should pump your brakes, and you should be looking into something like tuning or making sure that the proper volume of catalyst was put in there. I love to tie in the operating data that you plant guys measure to show you the benefits of tuning. So this data was provided from the plant, and what we decided to plot together was ammonia slip as a function of NOx conversion. Before the outage maintenance, this particular unit was struggling to get to the 90% NOx conversion that it needed. After maintenance and tuning, the ability of the catalyst to get even more than 90% conversion was achieved, and with an ammonia slip that's 1/3 of what it was while trying to get there. So this is a great case study to show how well tuning took a system to get even more performance.
Yeah, Andy, the black and white bottom line on this one is, in addition to the performance improvements you displayed on NOx conversion, we were able to save the customer $22,000 in annual ammonia consumption alone. So great immediate improvement here. Now to go on to case study 2, the Siemens unit. Andy?
Yeah, this is another great example. So the plant had contacted us and said, we know our ammonia flow is high, and coming out of an outage work, come on out and let's tune it. So for this unit, I don't have much to say here. It's a typical 501F, and they had all of you can see the scaffolding there. I guess that's a good takeaway. That would be something that you'd need to give access to the ports if you're not using a permanent grid. But this is another great success story. Original as found, we had an ammonia consumption rate of 340 pounds an hour. After tuning, we reduced that almost 100 pounds an hour. That's a huge ammonia savings, and their ammonia slip went from a number that's probably over 10 to well below their ammonia slip limit of 2.5. And then again, stack NOx stays the same. That's your set point. You guys all know that. I love these surface plots. So here, what we found when we got there is that the NOx towards the ceiling was real high. So this would be an indication that whatever valve is controlling that zone, we would need to open. And the after, because the ammonia is more interesting, but the after here is we're able to take that high spot out, but not completely. And that's kind of something that you need to realize. The real world isn't perfect. You're never going to see a surface plot be all one color. And that would be what you would want ideally. But that, you know, in this case, we had a great level of success, and this was the responding surface plot for NOx. The next one's ammonia. Look how great this turned out. So if any shade of red would indicate a value that was above their slip limit, you could see that we've about minimized that, where shades of blue would be under the ammonia slip limit. You saw from the general numbers that we got in the beginning of this case study, you know, that's what happens when you get rid of 100 pounds an hour in the duct at a time. You just get results that are this great. Another way to look at this in the next slide is ammonia efficiency. So again, this is something that you can look at in the plant, which is a ratio of the ammonia fed per NOx converted. So in an ideal world, like in a laboratory, if you were running this test reactor, your ammonia efficiency would be very close to 100 because you're able to put a ppm of ammonia right next to a ppm of NOx. In this particular case, for this unit, you know, it's not as high. But what I want to focus on is the level of improvement. So as found, and, you know, for the first traverse, you're hovering around under 50% ammonia efficiency. And then by the end, this particular unit was able to get up to almost 65%. So that 15% jump is something that you can see, and the plant's seeing the drop in ammonia consumption. So this one also had a great turnout for the plant to save. And
the efficiency is the name of the game here for sure, like the title of that slide. Not only did we fix this unit and get it back to compliance, but we were able to realize a plant savings of over $40,000 in ammonia, effectively killing two birds with one stone. They were able to run better and save money at the same time. Efficiency equals dollars. I've had the opportunity to review, you know, the definition of a lot of these systems, the implementation of some of these systems, and design, along with how to read results afterwards. And obviously, you know, we'll be able to have more in-depth, you know, discussions one-on-one, and be able to field any questions that you might have. But to just, you know, come full circle and identify some of the key takeaways here. Very important to note that tuning has multiple benefits on the operation side and on your bottom line. Implementing a permanent sampling grid enables you to do way more, much better, more efficiently. Also, as Andy pointed out with those pictures that were not pretty, with the ammonia buildup, oxidation, etc., scaling, it's very important to start with a clean slate and clean your AIG prior to any tuning, so you can get the proper results. And finally, a system balance will pay dividends, and it's not expensive to do, nor do you need a big outage or a big turnaround to install one of these. So we greatly appreciate everyone's time and investing here to you know, listen to our webinar and to watch our presentation. We hope that we addressed a lot of your questions up front. I do see that we've got a few questions here to field. So let's see. Okay. Question one. I have a series of ethane furnaces with SCR catalyst. Can those be tuned? Absolutely. Andy, do you have specific input on that?
I have lots to say. Thank you. Absolutely. So depending on what your NOx conversion requirement is and what your slip requirement is, I'm also possibly familiar with these units, and all come down to where are your ports and do you need a permanent grid? Because if the maximum size sample probe that you can put in there would be, you know, that you can get in the duct is 15 foot. So let's say your SCR reactor geometry is you have 3 ports on the skinny side, which is like, 10 foot wide, and then your reactor is 40 feet long, but you don't have access to put ports in on that 40-foot side. This is a home run scenario for a permanent grid. So you'd put the grid in, and then you have, you're at your permanent scaffold location with the 3 ports that exist. You could sample the entire length of the SCR catalyst that way.
Excellent. That was a great question. Well covered, Andy. Here's another good one from the Southeast. Would sampling for ammonia slip at the Hersig exhaust stack be a good indication that an AIG tuning is needed, or would the ammonia plating out on the tubes throw off the results?
I think that measuring your ammonia slip at the stack is a good indication if your plant doesn't have to do it continuously. And that's kind of what happened for case study 2, is that plant isn't required to measure ammonia slip continuously, did some diagnostic testing and said, we're looking to increase some efficiency here. So that would be a great indication that your unit would be a prime candidate for tuning. The other thing that we would want to look at is what your inlet NOx is and what your relationship to your ammonia flow and inlet NOx is.
Okay, fantastic. It looks like we hit a chord on the ROI. A lot of folks are trying to justify doing it here, and I'm going to try to cliff note because some of these questions kind of overlap. How does the ROI of AIG tuning compare to SCRs on regular boilers, assuming the same conditions and environmental limits? Our boiler has an SCR that is much smaller than one on a standard Hersig. So,
well, great question. In terms of ammonia consumption, a unit with an exhaust flow that's like 15 million standard cubic feet an hour and an inlet NOx of 25 would only have 100 pounds an hour of 19% aqueous flow. That would be, scale that up to like one of these G-class turbines, and their flow rate is 400 or 500 pounds an hour of 19% aqueous ammonia flow. Just on those, and that's a turbine that's 5 times larger. So the amount of ammonia that you save is, what Steve factors in, and it would take more to in a smaller unit to see the benefit. But the other point that Steve made in the very beginning that's difficult to quantify inside of the confines of this presentation is you're using more of your SCR catalyst. So that equates to additional life. So if you're getting that ammonia dispersed better across your catalyst face, that could be, a year or 2 years extra. That would be something that we'd have to look at on a case-by-case basis, but that claim is out there. It's something that you could do.
Here's a question on AIG tuning process without a sampling grid. How do you safely perform a traverse of an online Hersig? Wouldn't the gas be under a positive pressure?
It is. And typically what happens is the stack testing unit that you bring in, they're prepared for this because they're doing the same thing at the stack. So when you're performing a RADA or a compliance test, it's the same procedure. So they have safety measures in place to block the flow around the probe so that none of the positive pressure hot gas is escaping, or they're protecting their bodies from it.
Right. And this one kind of goes in line with that, asking about the tuning process. Is there anything that you can do to adjust ammonia flow laterally across the ammonia lance? That's
a tough one. So we've done that work, but it's not online. So in cases where The problem is across the tuning zone, had to re-engineer the lance or go in and split the lance. There's a design I can think of, I believe Peerless makes it, where they take the long sections and split them out purposefully so that you're not trying to tune a zone that's 40-foot long. They split them into 220s. So something like, if your problem is that bad, re-engineering may need to be necessary, but we would solve it. We would learn that is the issue with some traverse testing.
Good, let's see. Okay, here's one on timing. How long do you expect the tuning to take on an average 7FA?
Well, I like 2 days. Recently, I was in a scenario where the plant was really hoping that we could get it done in 1 day, and there's just a calamity of issues that come up during tuning that are all easy to overcome, that just exist in this complicated of a procedure. There's a lot of moving parts. The plant has to operate at the same load. If there's any kind of blips in operation, we have to stall the test and wait till the system is back online, stable, et cetera. If there's a cal that's required, we wouldn't be able to test during the calibration period. And then there's stack testing issues. If you're in a hot zone, you're working with a glass probe. When you pull that probe out of the duct, it gets brittle. Sometimes they break. You break the probe, then it's required to back up and make sure that your audit gases that the stack tester would bring are still measuring what they need to measure, so that when they put this new probe in, you're not getting new values that may conflict with the previous data you got with the old probe. So there's a little bit of, I would call it just growing pains of a day of tuning that exists. But in 2 12-hour days, you could usually get a great tune as a result. Now, in other cases where you want to try to fit an all-season tire tune to your unit, where you have great baseline performance, but also want to adjust your ammonia flow so that you see good results at turndown, that would require some extra time. And we've done this for a few clients along the way, and they love this.
Fantastic. I'm going to pose another question here. Let's see. We got a particular plant that ammonia slip is the concern primarily, not necessarily ROI. They're concerned with the impact of ammonia slip on the tubes and performance losses due to ABS, or ammonium bisulfate fouling. Are there better ways to correlate the AIG tuning with less tube fouling and performance losses?
If we had more than 45 minutes. That's the other benefit of ammonia tuning. So the less ammonia slip you have coming out of your SCR catalyst, the less ammonia is available to react with the sulfur in your exhaust stream to form ammonia sulfates. So that's the other benefit of ammonia injection grid tuning that is just a whole separate webinar that we could get into.
Yeah. We also have some interest on asset life or CapEx, the CapEx investment for the SCR. In the example, Andy, where ammonia slip dropped from 10 ppm to under 3 after you tuned, do you have an estimate of what the extended life of that catalyst would be from that change?
Well, I didn't test the catalyst, but in a broad sense, I could say that if the plant was unaware of the benefits of ammonia tuning, they could have replaced the catalyst just when they saw that the ammonia slip was too high. So then it would have come out at that point, let's call this, 2018 or whatever, and then it's still in service now. So you would need catalyst testing to accurately provide the information on where end of life is now. But knowing your real life RMS distribution of ammonia is vital to projecting catalyst life. If you assume the same real world conditions that don't exist, the same lab conditions that don't exist in your real world, you'll never hit that number correctly. I've seen two units right next to each other not be able to tune the same way, and with the same catalyst test results have different estimated lives.
Okay, the questions keep flying in. So I'd like to say that this is 20 questions, but we're 11 in so far. Appreciate everyone's interest here. Correlation on a theoretical efficiency. Is ammonia efficiency a function of the theoretical efficiency in the lab versus the field? How would you monitor for ammonia efficiency? And you touched on this in one of your slides here, Andy, but looking for a little bit more specific explanation here.
Yeah, I mean, if you know your exhaust flow, you can calculate the to your SCR ammonia ppms based on your ammonia flow rate. And then you would, in this case, need to know what your inlet NOx is. And then obviously what the stack NOx is. So then you would have a ratio of your inlet ammonia to how much of your NOx you converted across the SCR catalyst. So that's a measure that Environex routinely performs when working with plants to project catalyst life or determine where a unit's at in terms of benefits of tuning.
Okay. Covering and analyzing the analyzing process, are ammonia slip monitors and pre-catalyst analyzers required for tuning?
No, we'll take care of all that. So the stack tester would measure your ammonia slip at the stack before or after. I mean, preference is after to let you know of where we're going to leave it. And then also a few times during the traverse testing exercise, measure what the NOx is before the SCR. So we'll be able to put all of the graphing that you see together that we showed today, like the surface plots, we'll be able to put all that together and we'll measure those values during the tuning. So you wouldn't have to worry about buying those analyzers just for the sake of tuning. Though I would argue the inlet NOx analyzer is key in understanding why your SCR has certain operational times where it doesn't respond as well, and that will give you an indication why.
Fantastic. Looks like we have two more so far, but they keep coming in. I appreciate you taking the firing squad on here, Andy. Here's a great one. Is it typical to do a retune on a unit on a changed SCR design? I think that this one is very direct and important. It's right, great aftermarket question. Whether you're changing any major variable from your lances to your catalyst to turbine upgrades themselves, every factor changes there, and you certainly want to, retune. Your gas path might change. Your pressure is going to change. There's a million different things to consider, and you definitely want to retune. Here's another question. Regarding units with inlet conditioning, i.e. fogging or wet compression, how have you seen changes in performance of SCR tuning setups with and without water injection? Let's see.
So I've done lots of versions of this over the years. It's a great question because you're definitely changing the bulk flow of the catalyst when you're fogging and especially with removing water injection. You'd want to traverse both and come up with a tune that would probably make them both happy, because trying to adjust the valves daily is problematic. You'll never get exactly where we had left it during the tuning exercise. You'll never get that back. So once you find the sweet spot in a tune, you want to not touch those again. So to answer the question of what do you do when you got two operating modes, I've done it for base load and turn down. I've done it for SCR catalyst systems where the temperature coming out was hot enough, or was cold enough rather, where you could do a tune with the tempering air fans on and off to come up with an optimal tune that way. And this wet compression fogging is no different. So what we would do is we would traverse the duct in one of those operating modes and then do the same thing in the other operating mode, and then come up with whatever is the optimal for both. It won't be the best. It's like an all-season tire. If you have a summer tire and a winter tire, they're way better in their respective seasons, but the all-season tire is what you need if you don't want to go buying two sets of rims for a Honda Civic.
Good analogy. A lot of the questions we're answering might be on older units here. We have a new question here on new boiler install with SCR. Would you expect to need 2 days for commissioning the SCR, or would it take longer? So I don't know if that question is pertaining to tuning or sampling grid specifically. Andy, what's your guesstimate on a new commissioning tuning timeline?
It's going to be size specific. So if it takes 5 minutes a test sample point and you have 40 samples, that's going to be our 2 days of tuning. But there was a question earlier with a significantly smaller SCR, and if you're talking about a duct that's only 10 by 10, for example, it may not take 2 days. But I still like to budget 2 and then see where we end up. If you're talking about an enormous application where we're doing 80 traverse test points, 2 days won't be enough. But for I glanced at the audience list, I don't think many people are in that category. I think it would all be in the 2 or less. But the people that would be less, I'd have to take a good look at what the system is, how small it is, how many.
Is it fair to say, no matter what the size, that a sampling grid helps you reduce the time?
In all cases, that is true, because you're not moving the probe up and down the elevation. So if you have a permanent sampling grid, now you've reduced the stack tester costs because they don't need a third person, and you're just bouncing from point to point in that flange network that Steven showed the picture of earlier on in this presentation. You're able to get a lot more information that way. I still like to budget 2 days, again, because you never know what kind of operational issues can come up in day one. Everyone learns a lot during day one.
Great. I just checked the chat board. It looks like there are some questions up there, as well as the Q&A area. A lot of fantastic questions. And the turnout was amazing. We appreciate everyone tuning in. As you can see here, my information along with Andy's is posted. If you have any questions, follow up at all, please feel free to reach out. And outside of that, I hope everyone has a great weekend, and please look forward to our next webinar series invite, which will be this time next month. Have a great weekend, everybody.